Hello, everyone. This presentation will be about an efficient algorithm for multiversion garbage collection with good bounds on time and space. Multiversioning is a widely used technique. It has been used in database systems, software transactional memories, concurrent data structures, and so on. In fact, most modern database systems use some form of multiversioning. The basic idea behind this technique is to keep around historical versions for each object. One of the challenges is managing the space usage. To avoid running out of memory, versions that are no longer needed have to be identified and reclaimed. This is called the multiversion garbage collection problem, or MVGC for short. This problem is interesting to study from a theory perspective, but it's also important in practice. Several studies from the database community have found that this garbage collection step can actually be the bottleneck in real-world workloads. So the question that we're interested in answering is, how do you garbage collect efficiently for multiversioning? Our main result is a solution to this problem that provides strong theoretical bounds. In terms of time complexity, our MVGC technique is weight-free and uses only constant time on average to reclaim a version. And in terms of space complexity, it maintains roughly a constant factor more versions than needed. So we essentially get near optimal time complexity with near optimal space usage. Our solution is also very general, and it can be applied to a wide range of multiversioning schemes. Several earlier solutions have been proposed, but to the best of our knowledge, all of these solutions either use unbounded space or require time proportional to the number of processes. So achieving these time and space bounds was a challenging task, and it required multiple new components. Some of these components, for example, our range tracker and our doubly linked list, we believe have broader applications outside of this garbage collection problem. And we'll talk more about these in future slides. So I'll first give a quick recap of what multiversioning is and why it's important. So as previously mentioned, multiversioning means keeping a history for each object. And these historical versions are usually organized in a linked list data structure, one per object. Updating an object involves adding a new node with a new value to the head of the linked list. Each value is also tagged with a timestamp representing when it was written. We won't worry about the specifics of how these timestamps are assigned because that differs from implementation to implementation, and it doesn't affect the garbage collection step. The main advantage of multiversioning is that it lets read-only operations obtain a consistent view of the objects while at the same time not blocking update operations. Examples of read-only operations include range queries or scanning a database, and these operations can often take a long time to complete. So it's important that they do not delay updates. To see an example, suppose a read-only operation starts and is assigned a timestamp 3. It can see a consistent view of the two objects by reading the versions highlighted in orange. While it performs these reads, the objects X and Y can be concurrently updated by other processes, and these updates do not have to wait for the read to complete. So multiversioning essentially provides an efficient way of taking snapshots across multiple objects. The disadvantage of maintaining these old versions is that they take up a lot of space, so we have to find a way to garbage collect ones that are obsolete. Note that traditional garbage collectors do not solve this problem because all the old versions are still reachable by following pointers, so none of them can be automatically collected. This raises two main questions. How do we know which versions are obsolete, and how do we safely reclaim them? To answer the first question, the most recent version of each object is obviously needed, and among the old versions, some may still be needed because they can still be accessed by read-only operations. Read-only operations are assigned a timestamp when they begin, and we can think of them as reserving vertical slices in time. For each object, the most recent version to the left of a vertical line is needed, and all others are obsolete. So ideally, we would like to sort in the version list so that they only contain the orange versions, but this is very hard to do precisely, so we usually allow for some slack. Let's take a look at some existing solutions to the multiversion garbage collection problem in a bit more detail. The simplest and most popular solution is to use some form of epoch-based collection. This involves keeping track of some point in time such that all operations that started before this point have completed. In this diagram, this is represented by the red line. Any version that was overridden before the red line will never be accessed again, so they are safety free. The big advantage of epoch-based methods is that they are fast and easy to implement. The disadvantage is that they cannot collect any obsolete versions that were newer than the oldest read-only operation. So if a read-only operation crashes, then the space usage can grow without bound. And even if crashes don't happen, if you combine large read-only operations with high update frequency, you can get very high space overhead. To deal with the drawbacks of epoch-based collection, several techniques have been proposed that are able to reclaim intermediate versions. These are GMV, HANA, and Steam. However, in worst-case executions, these techniques require at least omega p time to collect each version, where p is the number of processes, and we are aiming for constant time on average. Also, they might keep around p times more versions than necessary, and we are aiming for roughly a constant factor more. These are the three main steps for garbage collecting old versions. And to get our desired time and space bounds, we had to come up with new ideas for all three steps. So for the first step, we implement a range tracking data structure, which stores a set of old versions and periodically identifies and returns ones that are obsolete. For the second step, let's say we know that this node n is obsolete because it was returned by the range tracker. In order to unlink it, we first have to know its parent. Since the parent changes dynamically over time, we track this information by making the version list doubly linked. To splice out the node n, we just want to make its two neighbors point to each other. The challenge is that while we are doing this, another process could be trying to remove n's neighbor, and we have to properly synchronize the two operations. We could use an existing algorithm for concurrent doubly linked lists to solve this problem, but that would break the constant time bounds we are aiming for. So our contribution here is a more efficient algorithm for remove, which takes amortized constant time rather than amortized order p time. Finally, step 3 is about safely reclaiming the memory of unlinked nodes. After a node n is removed, it's not safe to reclaim its memory right away because another process in the middle of traversing the version list might have paused on this node. This is a well-studied problem that's sometimes referred to as the safe memory reclamation problem. Standard solutions like reference counting and hazard pointers would work, but they do not maintain the bounds that we want. If you apply hazard pointers to a linked list, then you sacrifice weight freedom on traversals. And if you apply reference counting, then you sacrifice space bounds. So we came up with a memory reclamation scheme that avoids both of these issues, and it's specifically designed for our doubly linked list from step 2. So now we'll go into each of these steps in more detail. So as mentioned previously, the first step is handled by our range tracker. This data structure basically gets a simplified view of this diagram. For each old version, it stores a triplet, which includes the timestamp that the version was created, plus the timestamp that the version was replaced. I'll represent these triplets using this new icon, and the contents of the range tracker would look something like this. Some of these old versions might have already been returned, so there could be gaps in the diagram. In addition to these triplets, the range tracker also knows about the timestamps of the ongoing read-only operations. These are stored in an announcement array data structure. The key operation supported by the range tracker is called deprecate. It is responsible for adding a new triplet and also for returning a set of obsolete versions. The challenge is implementing deprecate so that all of this can be done in amortized constant time. So note that the obsolete versions are exactly the intervals that are not intersected by any of the announced timestamps. Locating these intervals is a very general problem that shows up in other places as well. For example, memory reclamation techniques like hazard errors and interval-based reclamation. In general, if triplets can be added anywhere in the data structure, then this problem would be very hard to do in constant time. But luckily, our problem is more well-behaved. We can make the observation that newly added triplets always have higher end timestamp than older triplets added by the same process. And this allows us to store the triplets sorted by end timestamp, and we'll see why this helps in future slides. Consider the following key problem. Given a triplet in a sorted announcement array, how long does it take to check if the triplet is obsolete? The fastest way to do this would be to binary search for the end timestamp, and then compare the previous element in the announcement array with the start timestamp. If the start timestamp is larger, then the triplet is obsolete, and otherwise it is needed. So overall, this takes order log p time, which is too slow for our purposes. However, it turns out that checking for a batch of triplets is cheaper as long as the batch is sorted by end timestamp. This takes advantage of the fact that you can binary search for all the endpoints in the batch using a merge operation, which takes linear time. Then you would do the same steps as before, and you'll find that the rightmost triplet is obsolete. Overall, this took order p time, which means constant time per triplet. This is a key substep of our algorithm, and the only difference is that we actually use batches of size p log p to cover the cost of scanning and sorting the announcement array. This will be an overview of how our range tracker works. Each process maintains a local list of triplets. Most deprecate operations simply append a triplet to this local list in return. When the local list reaches size p log p, it is pushed onto a shared queue, and then two lists are popped from the shared queue to prevent it from getting too big. Next, the process splits the two lists into needed and obsolete versions. As described in the previous slide, this is done by scanning the announcement array and merging it with the two lists. The obsolete versions are returned, and the rest are added back to the local list. So this is a high-level picture of how our range tracker is designed. So now that we've identified a set of obsolete versions, the next step is to remove them from the version list. Recall that the challenge here is that there might be multiple processes removing at the same time, so we need to synchronize between them efficiently. Removing two adjacent nodes at the same time is dangerous because if it's not done carefully, it could corrupt the structure of the linked list. And in our algorithm, we avoid this problem using an idea from parallel list contraction. So the idea is to store a depth value in each node in the version list. So this depth information is stored alongside the timestamp and value fields. This depth will be used to define an implicit tree as follows. So first, the smallest depth is picked out and made the root of the tree. And then we build the tree recursively on the two sides. And eventually we'll end up with a structure that looks like this. So the key idea is to only remove nodes from the version list if it is a leaf in the implicit tree. And the important property is that leaves in the implicit tree will never be adjacent in the version list. So we'll never run into the problem that we had before. So it's important to note that this implicit tree is not actually stored anywhere in memory. It's just a helpful way for us to reason about the algorithm. So now let's look at the remove algorithm in more detail. Let's label these three nodes X, Y, and Z, and suppose we're trying to remove X. The first step is to mark it for deletion, and then check if it's a leaf in the implicit tree. This can be done by looking at the two neighbors of X and making sure that they have lower timestamp than X. In this case, they do, so X can be unlinked. And now if we're removing Y, we'll see that Y is an internal node, so we keep it in the tree for now. When one of the leaves gets spliced out, that could potentially make its parent in the implicit tree a leaf. So then it's responsible for recursively going up the tree and splicing out its parents if needed. So in this example, after Z gets marked and removed, Y becomes a leaf. So whoever spliced out Z is responsible for splicing out Y. And that's the high-level idea behind the algorithm. So the nice thing about this algorithm is that it takes amortized constant time and worst case order L time, where L is the number of nodes appended to the version list. But the disadvantage is that there's space overhead because some of the internal nodes cannot be removed. So let's look at how bad the space overhead can be. If the tree is full, then it's just a constant factor overhead. But after some removes happen and the tree becomes more sparse, the situation gets worse. So imagine all the internal nodes are marked, but the leaves are not. Then each unmarked leaf could prevent the removal of log of L internal nodes. So the overall space overhead is a factor of log L, which is too high. So to avoid this, we need some way of removing these internal nodes, but we have to be careful which ones we pick to remove, because recall that it's dangerous to be splicing out two adjacent nodes at the same time. So let's say Y is an internal node. These diagrams represent the conditions that Y needs to satisfy before it can be spliced out. So the first thing is that the depth of Y has to be in between the depths of its two neighbors. And also the depth of the neighbor that's lower down in the implicit tree has to be unmarked. And if these two are satisfied, then we can safely splice out Y. And the reason why this is safe is that there can't be a concurrent splice on X because it's unmarked. And there also can't be a concurrent splice on Z because it's an internal node and Y is marked. And to make sure that to make this argument work, we have to make sure that X is not marked for the entire duration of the splice on Y. And we do this by installing descriptors on X and using some fairly intricate helping techniques that I won't have time to get into in the presentation. So let's go back to the example from before. If we apply these two new operations recursively to get rid of internal nodes, we'll eventually be left with a tree that looks like this. Note that some of the nodes can't be removed using the new rules, but we can show that there's at most a constant fraction of nodes like this. And this is what ensures that we get reasonable space bounds. So using these high-level ideas, these are the time and space bounds that we are able to achieve. And again, the interesting thing here is that we were able to implement remove and amortize constant time, regardless of the amount of contention. So that's it for step two. Unfortunately, I won't be able to cover step three in this presentation, but if you're interested, all the details can be found in our paper. So overall, across all three steps, we ensure that the time required to reclaim a version is order 1 on average, and we ensure that this process is weight-free. In terms of space bounds, we ensure that the number of unreclaimed versions is proportional to the number of required versions plus an additive term. And more specifically, the bound looks like order of n plus p squared log p plus p log l, where n is the high watermark number of needed versions throughout an execution, p is the number of processes, and l is the maximum number of versions added to a single version list. To put this into perspective, let's start by looking at the p log l term. L can technically continue to grow as more versions get created, but log of L grows very slowly. Assuming you can create 1 billion versions a second and you continue doing this for 1,000 years, log of L will still be less than 65. So the p log L term won't be too big in practice. For the p squared log p term, a lot of memory reclamation techniques like hazard pointers have p squared overhead, and this is fairly standard. We are off from this by a factor of log of p. So in large data structures, the number of needed versions is usually going to be much larger than the additive term. And in this case, we just keep around a constant factor more versions than needed. So in conclusion, our paper presents a theoretically efficient solution to the multi-version garbage collection problem, and this required developing new techniques for all three steps. We are currently working on a practical version of this algorithm, and the preliminary results look promising. So that's it for this talk, and thank you for listening.